Hello, this is Wei Luo from Nanyang Technological University, Singapore. Very nice to meet you all in QCrypt 2020. And this is my colleague, Xiao.
Hello, everyone. My name is Holly. Nice to meet you.
Okay, today we would like to introduce our work on chip-based QKD systems. Yeah. Okay, let's go. And first, I would present our recent progress on the integrated chip platform for MDI-QKD. After my presentation, my colleague Cao Ling will show his work about on-chip CV-QKD. In this talk, I will first introduce the background for chip-based QKD, then our MDI-QKD chip implementation and experimental results, and finally a conclusion. As we know, being portable and cost-effective has become a mainstream in the information technology nowadays. Apparently, conventional bulky optical systems no longer satisfy this increasing demand. So we can see in recent years, more and more researchers have been involved in the studies of embedding quantum information applications into scalable integrated devices. Until now, a range of platforms have been developed for integrated quantum photonic applications, including quantum computing and quantum communication. Among these platforms, laser writing silica, silicon on insulator, indium phosphide, and silicon oxynitride have already been adopted in the QKD applications. For example, researchers from University of Toronto presented a silicon-based optical transmitter for polarization-encoded QKD in 2016. Almost in the same time, researchers from University of Bristol also demonstrated hybrid integrated QKD systems, which were able to implement multiple QKD protocols with gigahertz clock rate. Other than DV-QKD system, attempt to achieve integrated CV-QKD system has also been made. In 2019, our group demonstrated a silicon photonic chip platform for CV-QKD. The proof of principle experiment indicates the system was able to produce positive key rate over 100 kilometers. For further development of chip-based QKD system, we are looking at the integration of measurement device-independent QKD. And MDI-QKD is very suitable for integration because Alice or Bob only needs a transmitter and shares the single photon detectors in the untrusted relay. It can be easily extended to a stud-type network. That means the integration of transmitter will greatly reduce the cost for extending the QKD network for multiple uses. Of course, photonic integration also benefits the MDI-QKD server. The MDI-QKD server can be integrated step by step. First, integrate the passive components, and then active components like optical switch. Finally, we can integrate the single photon detectors and realize fully chip-based server. Based on this idea, we developed a chip-based MDI-QKD system by integrating both transmitter and server chips. For transmitter chip, we integrate two intensity modulators, two phase modulators, and one path-to-polarization converters on it. The first intensity modulator is used to create signal and decoy states. It can provide extinction ratio over 30 dB. The first phase modulator is used to implement random modulations of input pulses. The second intensity modulator and the second phase modulator, including the path-to-polarization converter, they form the polarization state encoder. By tuning the two modulators, we can generate the horizontal, vertical, plus and minus states required in the BPA-T4 protocol. In terms of server chip, we integrate all the passive components, including one 50 by 50 beam splitter and 2 polarization beam splitter on the chip. This picture shows the fabricated silicon photonic chips and a chip after packaging. For transmitter chip, we adopt grating coupler to couple the coherent pulses generated off-chip. The encoded polarization states are coupled out by a tapered waveguide coupler because it can support multiple polarizations and provide much lower loss, about 1.2 dB. For server chip, the two inputs are 2 tapered couplers, and the outputs are 4 grating couplers. We calibrate the MDI-QKD transmitter chips using a fiber-based polarization alignment system. The calibration setup consists of a 50 by 50 beam splitter for passive selection of the measurement basis. One output of the BS is connected to a PBS to measure the horizontal and vertical polarizations, and the other output is coupled to a PBS to measure plus and minus polarizations. We scan the voltages applied on the polarization state encoder. The results for each polarization state are shown in this figure. From the figure, we can see the transmitter chip is capable of providing polarization states with extinction ratio over 20 dB. Highly meets the requirement of the MDI-QKD demonstration. Here shows our setup for proof of principle demonstration of chip-based MDI-QKD. For each transmitter, a pulsed modulated frequency lock laser is used as coherent light source and coupled into the silicon photonic transmitter chip. The clock rate here is only 0.5 MHz because we use thermal optic modulators in proof of principle demonstration. It can only support sub-megahertz modulation. And later, I will show our high-speed chip with carrier depletion modulators, which can operate at gigahertz clock rate. At server side, we adopt single photon detectors with 25% detection efficiency. And the attenuation of standard single mode fiber is emulated by optical attenuators. In the demonstration, we implement a 4-intensity decoy state MDI-QKD protocol, and the intensity are determined according to the configurations of our chip-based system. And the corresponding probabilities are also listed here in this table. With the finite key effect taken into consideration, the key rate of the protocol is given by this equation. We measure the total gains and error gains in experiments, and then analyze the secure key rate of our chip-based MDI-QKD system. From the results, we can see the fundamental visibility of our chip-based system is about 48%, close to the theoretical values. And the quantum bit error rate is observed about 0.67% in Z basis, and about 25.6% in the X basis, which is also comparable to the theoretical values. And the key rate per pulse of our system is calculated to be about 2.9 times 10 to the minus 6 over a distance corresponding to 50 kilometer fiber length with 25% detection efficiency. And this value agrees well with the simulation results. And we can also see it's comparable to the results from other MDI-QKD studies, including 2 recent chip-based MDI-QKD systems. Previously, I mentioned the high-speed transmitter with carrier depletion modulators. Recently, we have fabricated the chip and completed the chip packaging. We characterize the high-speed modulator on the chip. And we can see from the results, the modulator has a static extinction ratio of about 30 dB. And the dynamic extinction ratio is over 20 dB at 1.25 GHz and also 2.5 GHz. The S21 figure indicates the bandwidth of the modulator is over 17.5 GHz. This data supports the transmitter is able to operate at 1.25 GHz and higher speed. In conclusion, we have developed an integrated photonic chip platform for MDI-QKD and demonstrate the proof of principle experiments. In detail, we design and fabricate both transmitter and server chips for MDI-QKD using silicon photonic technology. And the proof of principle demonstration indicates our chip-based MDI-QKD system can provide polarization states with extinction ratio over 20 dB. And the QBR of the system agrees well with the theoretical values, which indicates our system performs well. And the Q rate per pulse of our system is about 2.9 times 10 to the minus 6 over a distance corresponding to 50 kilometers. In the future, we will continue to demonstrate high-speed transmitter operating at gigahertz clock rate, and also demonstrate chip-based MDI-QKD system with better performance. If you are interested in our work, please take a look at our newly published paper in PR Apply in this year. Okay, in the next part, my colleague Calim will present his work on on-chip CV-QKD system. Calim, please.
Okay, hello. In this talk, I will speak about time and the polarization-multiplexed continuous variable quantum key distribution. I will first give an introduction and objective of CV-QKD, then experiment setup and results. And finally, I will give a conclusion. By now, many experimental demonstrations have showed the feasibility of CV-QKD with coherent states. The experimental performance of these works have been evaluated in various settings and assumptions. The most famous CV-QKD protocol is the GG02 protocol, which is based on Gaussian modulation of amplitude and phase of coherent states, and homodyne detection of the channel output. In this work, we implement an on-chip continuous variable QKD system based on silicon fabrication technology. Time and polarization multiplexing enable signal pulse and local oscillator pulse share single fiber channel and provide lower crosstalk between signal and local oscillator layouts. Key components in this work are integrated on the chip. In the system, on any side, continuous wave coherent light source is coupled into transmitter chip by grating coupler. Then, three identical amplitude modulators generate loud pulse at a repetition of 5 MHz. An unbalanced beam splitter divides the pulses into local oscillator pulses and weak signal pulses. To realize the zero-centered Gaussian distribution, signal pulses are encoded by an amplitude modulator with Rayleigh distribution and phase modulator with uniform distribution. The signal pulses are delayed by an off-chip delay line and recombined with the local oscillator pulse by a polarization beam combiner. Then, signal and local oscillator pulses are sent to bulb via a long fiber channel. On bulb side, electronic polarization controller and a photon detector are used to optimize the input of polarization beam splitter. On local path, an off-chip delay line corresponding to the one used by Alice allowed for a time superposition of both the signal and the local oscillator. A fast modulator random measure signal quadrature. Then, the signal pulses and the local oscillator pulses interfere on homodyne detector. This picture shows the fabricated silicon photonic components and the chip after packaging. All the components in CV-QKD system include amplitude modulators, phase modulator, photon detector, polarization beam splitter, homodyne detector. These components are designed and fabricated using silicon fabrication technology. On transmitter chip, loud pulse is generated by amplitude modulators. In the setup, 3 identical amplitude modulators based on p-n junction are cascaded and modulated simultaneously by arbitrary waveform generator to realize high pulse acting ratio. This line chart shows that the static pulse acting ratio of individual amplitude modulator is up to 35 dB with 0.9 volt. The dynamic modulation of amplitude modulators are tested. 3 amplitude modulators are pulsed square by square signal with a duty circle of 20% and a frequency of 5 MHz. The picture above shows the pulse width from output of amplitude modulation is around 41 nanoseconds, and the rest time is around 5 nanoseconds. The pictures below shows identical and stable loud pulses can be generated in a long time. The dynamic pulse acting ratio at 5 MHz repetition is larger than 21 dB. In our previous work, single on-chip PBS at 50-50 nanometer only provides 25 dB polarization oscillation. To reduce crosstalk between a signal and the local oscillator louds, higher polarization acting ratio is necessary. So, cascaded polarization beam splitter is designed and measured. The testing result shows the polarization acting ratio of new structure is larger than 30 dB, which meets the requirement of polarization-multiplexing. The system noises are carefully measured to calculate the secret key rate. This line chart shows the different noise spectrum in the system. The electronic noise of the off-chip homodyne detector is around minus 87 dBm. The short noise is 7 to 10 dB higher than the electronic background noise, which corresponded to a 7 to 10 dB signal-to-noise ratio at the 2 to 10 MHz band. With modulation on, the measured output is 12.5 dB higher than the short noise, which we refer as a 12.5 short noise unit modulation. Till now, the parameters we have measured are summarized in the table. The table shows the efficiency, the detector efficiency, the modulation variance, pulse repetition, and coupling loss in receiver chip. To better implement long-distance communication using such on-chip CV-QKD system, simulation under different conditions has been done. The line chart shows the Hollywood key rate and distance relationship less than 100 km on different excess noises. Excess noise will largely reduce the performance of QKD system. When excess noise is larger than 0.03, the key rate drops down sharply. When the excess noise is 0.08, the key rate is only 0.89 kbps over 40 kilometers. Off-chip and on-chip home dyne detector are compared as well. This chart shows the performance of detectors are similar. Reconciliation efficiency is another element that affects the key rate. The chart shows the performance improvements arising from the enhanced reconciliation efficiency from 0.95 to 0.99. When reconciliation efficiency is 0.95, the key rate remains 33.9 kbps over 40 kilometers. To sum up, we designed and fabricated an on-chip time and polarization-multiplexed combined continuous variable quantum key distribution. The performance of such on-chip CV-QKD system is tested. The amplitude modulator for pulse generation performs well. Its static pulse exchange ratio is about 35 dB, and the dynamic pulse exchange ratio is about 21 dB at a repetition of 5 MHz. The polarization oscillation of on-chip polarization beam splitter is larger than 30 dB. We also analyze system noises, includes electronic noise, short noise, and modulation variance. Simulation of key analysis under different conditions is performed. The result shows the secret key rate remains positive over 40 km, even though in high excess noise or lower reconciliation efficiency. In future, we continue to do the demonstration of long-distance continuous variable quantum key distribution by on-chip time and polarization multiplexing. Our research is supported by Ministry of Education, Singapore, and the National Research Foundation, Singapore. That's all. Thank you for your listening.
Thank you. If you have any question, feel free to contact us. Thank you for listening.